Hey there, guess who's back? I mean, who did you think it was going to be? We're going to talk about Chapter 9, Thermochemistry, today. But before we do that, we have to start off defining some units, and it's kind of get an introduction to energy. So this is kind of going to blur into the lines of physics. Like, you're going to recognize some concepts from physics, especially joules and work, but we're putting it into a chemistry context now, just for kicks, or more than kicks. Well, there's cursive written on the formation of cyclopropane through carbene. I didn't write that, but it's there. It's invisible. Anyways, I love this whiteboard. It's like magic. First, what is a joule? A joule is a unit of energy, and it's the standard unit of energy. It is defined as kilograms per something squared. What is the thing? M squared? I don't know what M is, but kilograms per, I think it's distance over second squared. That's what a joule is. And the units can get kind of wonky, but all you need to remember is that it's in kilograms. So if you ever need to do a conversion, you have to do some multiplication. Joules, then we have a calorie. A calorie is another measurement of energy. Notice how this is a lowercase c. It is equal to 4.184 joules. And a calorie is used a lot in like organic stuff. And don't mix it up. It is 1 calorie for 4.184 joules. A kilocalorie, capital C, that's what it is equal to 1,000 calories. And the definition of these is, well, first, joule doesn't really have a definition besides that. It's just what it is. But the calorie is the amount of energy required to raise a gram of water by 1 degree Celsius. That is also equivalent to the specific heat of water, which we'll get into later. Uh, let's see if I remembered that correctly off my notes. Yup, it's energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Simple as that. So, after that, we get into kilocalories. Same thing. One other note, British thermal unit is just the weird British one. It's equal to 10,055 joules. And is literally the amount of energy required to raise a pound of water by 1 degree Fahrenheit. So it's just a calorie, but for weirdos. Which is why I'm going to erase it off the board right now, because no one cares. Yeah. After that, it gets a little bit more interesting. So we stay with that. We defined that. Calories can also be defined as food calories. Just make a note on that. Like 1 kilocalorie is a food calorie. And keep in mind that we will often be working in kilojoules. Let's say I have carbonate, CO3, plus vinegar, which I think is CH3 CH3COOH. So this is baking soda and vinegar. Have you ever done this? Have you ever taken baking soda and vinegar and put them together? Well, one, they release gas. They release, I think, hydrogen, whatever it is. But they also make heat. If you stick your fingers in, it'll be like, oh my gosh, that's warm. Why is that? That's because of thermochemistry. Each of these elements, or these substances, hold a specific amount of energy. And to get them to react, you do have to add a bit of energy as well. So, reactions. This is how reactions work. There are two types of reactions in terms of energy and heat: exothermic and endothermic. Endothermic. So exothermic reactions are reactions that release heat, where they have a bunch of pent-up energy, and when they react, all the energy dissipates because they have moved into a lower energy level. So the atoms are just fine. There's endothermic. These are the ones that absorb heat. So you can think about it like a box. Like my reaction is a box. So when I put energy into it, stuff happens, and if it keeps that energy, it's an endothermic reaction. If it releases that energy with a bunch more energy, it's exothermic. For example, a an explosion. Like if I have gasoline and I put a tiny match on it, I've added heat, but an immense amount of heat is released because of that. In contrast, I don't know any contrast ones off the top of my head, but fire is fun. But you can represent exothermic and endothermic reactions on a graph using energy. So, when you have an exothermic reaction, the energy level of the reactants is going to start about here. So this is going to be time, and this is going to be energy. I'm going to start up here. Now, to get the reaction started, because if they're sitting here, they're holding energy, but it's potential energy. It's not doing anything. So to get them started, you have to add a bit of energy. And it'll go like that. And then the reaction will begin here, the activation level. And then, if it's exothermic, it's going to release a ton of energy until it gets to the end. And then this will be its new energy level. So it'll start here, activate. So I'm going to use a new color for this. The activation energy is this amount of energy up to there that you have to add for the reaction to start. And then this is the total energy there. And then from here to here is the net loss of energy. So this is going to be a negative energy, a negative change in heat. We're going to use heat to refer to this for a while. And heat, by the way, is going to be measured in joules. So an endothermic reaction is the opposite in terms of energy. So draw the graph. An endothermic reaction is going to start really low, and it's going to have to get a huge boost of energy to get it to start, but then it will end with a higher level of energy. So this is T, energy in joules, and yes, that's endothermic because the starting energy is less than the amount of energy it ended with, and that's the difference between exothermic and endothermic. Simple enough. So we refer, well, the idea of thermochemistry is measuring the change in H, delta H, the amount of energy that has changed within it. Within a reaction or a system, the amount of energy that goes in is the same amount that's going to come out. If it releases it, like law of conservation of energy, energy is not created or destroyed. If energy comes in, it came from somewhere. If it goes out, it came from the thing, and the total amount of energy in the universe has not changed. So, after that, let's talk about systems. This is just some terminology. I think it's just system. Yeah, so oh yeah, so for a reaction, the molecules you're studying are the system, like I don't know, like the water and the tungsten. I just like tungsten. And then everything else that surrounds and interacts with the system is called the surroundings, which is important to know because in a closed system, nothing, uh, nothing comes in or out except for heat or energy in the form of heat. An open system is just like, I don't know, baking soda and vinegar, like in an open beaker. Air can come in, gas can be released, and heat just goes wherever it wants, it dissipates. Isolated system is where everything is just stuck inside a box and nothing can escape. Like nothing, nothing. Anyways, after that, change in energy, internal energy. Oh yeah, so the change in energy is what's important. E final to minus E initial. That's just an important idea. Just kind of skim through this because it's not really too complex until we get to our equations, or the important equations. So, I'm just going to erase this. Oh, there was one more unit I forgot to mention. The liter per atmosphere is equal to 101.325 joules. That will be important later, so just keep an eye on it. Uh, yep. So thermic and endothermic reactions. So for exothermic reactions, oh, first this variable change in heat is or better said, the change in energy is equal to the two ways that energy can enter or exit a system. Through heat, which here is going to be represented as Q, but is actually like delta H, plus W, where W is work, which is measured in joules. These are both measured in joules, by the way, because the change in energy is measured in joules. Heat is the obvious one that we're going to be talking about, but work is the less thought about one. You'd be like, what? How can a reaction do work? How can a system do work? This is when it like interacts with its surroundings to like do something. Think about like gas inside a balloon. If I heat the balloon, um, it's going to expand. So you can call that work, where it's performing on its surroundings. Uh, Another example could be like, let's say you have a piston that's like this, and it pushes down on a gas. Work is being done on that gas, and because of that, the energy within that gas, the potential energy, is going to increase. And if the gas pushes back and the piston goes up, that means the gas is doing work, and that's energy released. Um, So yeah, so the change in energy is equal to Q plus W. If heat is lost, that's negative. If work is done by the system, that's negative because the energy is leaving the bank, you could say. It's changing heats can be positive if it's endothermic, if it takes on energy, and it's the work. Times the specific heat times the change in temperature. Okay, so what are these things? What is specific heat? So specific heat comes from the concept of heat capacity. So imagine I have a big block of tungsten. What is the amount of heat that I can pour into this thing before it starts doing stuff? Um, I'm pretty sure that's what it means. Where's the specific definition? Where is it? Where is it? Where is it? Specific heat. Oh yeah, so the specific heat is the amount of energy required to raise the temperature of a given sample of a substance by 1 degree. Uh, that's its specific heat. Heat capacity is how much heat a thing can hold. Oh no, how much heat it takes to raise it by 1 degree, sorry. So let's say I have a block of tungsten that weighs 30 pounds. Actually, let's say 30 kilograms. 30 kilograms. So if I want to raise the temperature of tungsten by a single degree, I'm gonna have to pour in a ton of energy, not relatively not that much, considering it's 30 kilograms to get it bunching. But what if I want to know like how much energy? So I can take a piece of it. If I take a single gram of my tungsten, this tiny little piece, and I put energy into it until its temperature has been raised by 1 degree, I can determine how much heat is proportionally going to work for this. And this is the specific heat. So there's the heat capacity, which is all of it, and there's the specific heat, which is the heat required to raise a single gram of it by that, which, if you remember, is a calorie for water, which is 4.184, which you have to remember. So that's what specific heat is, and the way you get it is by this equation, but rearranged. Uh, but for the basic stuff, the change in heat in a reaction is going to depend on its mass times the specific heat which is, and then times the temperature, which is essentially saying like how much is there to be raised? How many degrees did we go? And because it's per, we go 1 degree per gram, you multiply that by the specific heat, and boom, you have the entire change in heat for the entire reaction. And simple as that. Change in temperature is as easy as just being like T1 or T2 minus T1. And yes, it does matter if it is a positive or negative number in the end. Specific heat is always positive, by the way. And grams is always in grams. And then heat comes out to be in joules. So that's how that equation works. Change in heat, you can use that to calculate a bunch of different things. Specific heat for water is 4.184. If you have an aqueous solution, the specific heat is going to be the specific heat of the solution, no, of the stuff that makes it aqueous. Like whatever your stuff is dissolved in, that's the specific heat. So like water, if you have like salt dissolved in water, the specific heat is going to be 4.184, like water is. Um, Another important thing to know is when you have specific heat for an equation. So let's say I have um, CH3 plus O2 becomes H2O plus CO2. So I can say for every mole of CH3 that is put into this reaction, uh, given amount, let's say like 300 joules, is released. So that's going to be negative 300 joules. So when I go in this direction, if I use 1 mole of this, I'm going to release 300 joules of energy uh, just because of that. So what you can do is, if given the amount of moles there are, you can kind of substitute it in and be like, okay, change in energy per that. So if I do, if let's say I have like 30 grams of CH3, let's do the math. If I have 30 grams of CH3, how much energy was released in this combustion? So 30 divided by alpha C plus 3 alpha H is 1.99 moles. So all I have to do is multiply 1.99 by negative 300, because that's how many moles there were, and I'm going to end up with negative 598.6 joules. So in this explosion, I released about 600 joules of energy when I burned 30 grams of it, specifically 30 grams. Something in my nose. Yeah, so I released specifically 30 grams, or burns 30 grams, and that's how much energy is released. And the way I can also calculate that is like, first, I weigh it. Two, if I know well, I mean, it's just algebra. If I know different variables, I can calculate for the other ones. For example, if I know the change in temperature, and I know the grams, and I know the change in heat, and then I can calculate for this, and then I can calculate for how many change in H per mole if I just go in that order. So I plug these four into the equation, solve for delta H, and then delta H divided by moles, because the what is it? Delta H for the reaction times equals change in energy total. So you just divide the total by the moles, then you're going to end up with the change in energy for the reaction. And so that's like a unit. You could say it's like a unit reaction. Moving on, I think that's actually a lot of it. Molar heat capacity is just specific heat of the substance times the molar mass is equal to molar heat capacity. You should remember that. Gallons, 1 gallon is equal to, or 1 gallon equals 3.785 liters. Guys, I really don't think it gets much harder than this. Um, oh yeah, the gases. So gases exhibit work um, just by the change in pressure and the volume. So there's a formula where the work done, or the work in energy, whether it was released or not, is going to be equal to negative P times delta V. So negative pressure times the change in volume is going to be equal to the amount of work that was done on the system. If the work was negative, that means the system did work. If the work is positive, that means work was done on the system. But it doesn't matter if you plug it into this equation. You just plug it in with the sign, and you will be good. So delta E. That's what it is. This comes out as a unit called liters per ATM, which you have to convert into joules. It's not automatically in joules. And the way you do this is 1 liter ATM is equal to 101.325 joules. And yeah, one, 1 liter per ATM. Easy as that. You just multiply, and then all of a sudden you have your amount in joules, x joules, and then you can plug it into that equation. Is that on my formula sheet? Yes, it is on my formula sheet. Let's see if I have anything else. I literally think that's it. Review. Okay, two vocabulary words. Enthalpy and, what was the other one? Oh, evolution. Um, so the change in heat is enthalpy. Like if I say, what's the enthalpy for this reaction? That's just the change in heat. They're trying to trick you. If they say, if you're in a question, it's like, I did this and it evolved 300 joules of something, or 300 joules of energy. That's a negative. Evolve is an exothermic term. I don't know why. They just put that on the test to make you feel stupid, I guess. But if it says evolve, that means it's releasing energy. I hope I'm not wrong about that because I'm just gaslighting myself. Anyways, that's it. That's actually all my review done uh, for for this exam. So I really hope I ace it tomorrow. Wish me luck. I hope I survive. I'm gonna go watch a movie for another class. It's 11:15 and I still have homework. Yeah.